Good afternoon, everybody.
Good afternoon.
We're just going to set up a presentation sharing. If you could bear with us a few seconds, please.
Hi, James. Please share your presentation and go ahead, please.
Hi, yes, unfortunately, the Zoom is not allowing me to share the presentation. It is marked as disabled, so.
Okay, you can share now.
Very good, thank you. Bear with me 1 second. Okay, hopefully everybody can see those slides.
Yeah.
Great. So my name is James Denton. I'm a principal architect at Rackspace. I've been involved with OpenStack for the last 10 or so years and originally got started in the Essex release back in 2012. This is my colleague, Chris Breu. He's a senior cloud architect at Rackspace, and he's been involved with OpenStack for the last 7 years or so. For those who may not know, Rackspace is a multi-cloud solution provider with experience in a variety of cloud platforms, including AWS, Google, Azure, Oracle, and private cloud technologies such as VMware, and my personal favorite, OpenStack. In fact, I'm proud to say that we were one of the original contributors to OpenStack and continue to be involved in the OpenInfra community and are committed to the success of its mission.
Thanks, James.
Chris?
Yeah, for this slide, I wanted to talk about a journey Rackspace had with a customer around a large deployment of up to 5,000 compute nodes behind a single control plane or a single API endpoint. So this all started back in about 2019 when a customer in the industrial design field reached out to Rackspace asking for help on how to virtualize their current workload. Another colleague and I, we flew out to this customer and spent 2 days doing a design summit with them. During that summit, we learned a lot about the requirements, how they're currently using their physical infrastructure, and what their asks were. One of the biggest challenges they had was they were deploying physical nodes into a server farm that was then used to do computational computing against their software to figure out metrics, build times. If I make this change in the software, does it increase my performance or is it detrimental to it? But unfortunately, while they were doing this, they realized that the workload of their tooling on their physical nodes was leaving a lot of resources behind. And so they said, okay, let's start looking at virtualization. They had a couple extra customers come in there. They tried a couple POCs on their own. As everyone knows, OpenStack is really easy to install, but it gets a little complicated when it's time to tune the dials and turn the levers, kind of a thing. So Rackspace was involved. We went out to the design summit and we gathered the requirements. They wanted up to 5,000 compute nodes behind a single control plane or API layer, and it must be performant and sustainable and upgradable and just do what they wanted to do. So we took all those requirements back to Rackspace and we sat down as a team and we said, hey, I think the only way we're going to be able to do this is with Nova Cells v2. That will allow us to take all of their compute nodes, shard them into manageable sections behind individual cell controllers, and still give them a single API endpoint, which was really big from them because, think of like neutron security groups, images, anything like that. Having a single API endpoint that spans multiple cells up to 5,000 compute nodes was super beneficial for them. Currently, we have this deployed with this customer with over 3,600 compute nodes behind 14 cells. And we are using a single API endpoint. One of the things that was also super beneficial to them was the ease of use of using Nova to build their servers that would then become part of their farm. In the past, they were using tooling like Foreman, Cobbler to have to physically re-kick and lay down an OS every time they wanted to make an OS improvement or test out a new version of Red Hat OpenStack, Red Hat Ubuntu or any of the other supported operating systems. This led to a massive lead time for them to keep current or update their fleet. Like they would have to pull the nodes out of the farm, lay down a new OS, either via Cabra or Formalin, re-roll them into the farm, and then proceed to do their computational testing. With OpenStack, that meant we can now redeploy a server that becomes part of their farm in less than 5 minutes. It was a huge win for them. They saw a lot more agility in their workflow to be able to test newer operating systems faster and keep up with what their clients' demands were.
Excellent. Great. So let's talk a little bit about how we address this request. So as Chris alluded to, we took the requirements back to Rackspace and decided that Sales v2 might be the right approach. But let's compare that to the standard reference architecture for what we call Rackspace Private Cloud based on OpenStack. So having built these private clouds for some time, we knew that the reference architecture might not be up to the task. On the left is a pretty standard OpenStack reference architecture, quite honestly, with 3 control nodes, a couple of load balancers, and an X number of compute nodes. Those control numbers host all of the OpenStack services, including all of the API services, the database, message bus, and quite often Neutron objects like L3 routers, DHCP agents, what have you. Left as is, this infrastructure can manage hundreds of compute nodes. In fact, we have customers that run 400 or 500 quite easily. We can scale out some of those services to place database nodes on their own hosts, Rabbit on their own hosts, and often enough spin out L3 agents so that Neutron routers aren't contending with resources consumed by API services. There is a limit to this method of scaling though. In the case of Galera, for example, no matter how much horizontal scaling you might do, typical deployments have a single write master. And so the only way to scale that would be to scale up to a bigger node. But thinking that Sales v2 might be the better approach, I'll move to the next slide and we'll kind of demonstrate what that looks like.
Yeah, so when we were doing our design review at Rackspace, and we picked Sales v2 as our go forward path, we then got to thinking, okay, where are each of these services going to live? So we termed it master control plane as basically that top layer that hosts all of the APIs, the message bus, the databasing, and the load balancing or the HA proxy layer. We did this with just 3 nodes in each one of those categories. So we have 3 nodes for the APIs, 3 nodes for Neutron, 3 nodes for Rabbit, 3 nodes for Galera, and 2 nodes for the HA proxy or the load balancer. This is our master control plane or our single point of egress into this environment. Furthering that, we then broke each of those computes into what we call cells, right? So we have a cell control plane layer as well. On that cell control plane, we're also running some Nova services, some Neutron services, very select services, a Galera cluster and a Rabbit cluster, but we're cohabitating all of those services on 3 controller nodes. And then behind each control plane, we just picked an arbitrary limit of 500 computes. That was basically just done from a networking standpoint, so we could do /23s across the cells. And then so from a service standpoint, do we want to talk about that too real quick, James? Yeah, service standpoint, Nova, Neutron, Glance, Cinder, Barbican, all of those services run at the MCP level. And also Conductor, right? Because we have what OpenStack terms superconductor. We also run Nova Conductor at the cell level, along with the Linux Bridge agent or the Open vSwitch agent or any of your Neutron agents. But Neutron server does run at the MCP level.
Right, so it's important to note that in the Sales v2 design, a lot of the so we'll call them infrastructure services are localized to the cell. So most importantly, the database and the message bus, right? The compute nodes and the conductor communicate with their localized database and message bus resources. Neutron agents are localized to the cell. And the master control plane doesn't really know too much about them and will query them as needed. So in this design, when a user does something like an OpenStack server list, the Nova API in the MCP will query each cell to gather information and return it to the customer. The beauty of this design is that there is no longer, compared to Sales v1 anyway, the need to sort of replicate everything in the MCP. And in the case the cell does fail, the MCP just won't return the results for that cell.
Yeah, it enabled a little bit more fault tolerance. So like exactly like James' point, if we lose a cell, you don't lose API functionality. You simply lose the data from that specific cell.
And importantly, the control plane data, right? Data plane, we expect this to continue to live on through its respective data plane.
Yeah, you're right, James. So it is just the control plane information, right? You would lose, like in a cell v2 deployment, instance data is always stored at the cell level. That's where you'll get naming, the network, basically anything that's tied to an instance from a database standpoint will live at the cell level. So when you're querying, like, give me a list of all the instances across all the cells, if one cell happens to be down, you just will not be returned any results from that.
Right. Okay. So before we move on to kind of how this deployment went into effect, I think it's important to note that there likely aren't too many OpenStack-based clouds out there in the world running more than, say, one cell. In fact, the 2021 OpenStack user survey specifically calls out cell utilization in the deployment decision section of the report. Of the 272 respondents, 81% were listed as using none or one, which is sort of the default configuration for a post-Queens greenfield deployment. 7% of the respondents were listed as using two cells, which very well might mean cell 0 and cell 1, which is also really the default configuration. Lastly, only 11 are listed as using more than 10 cells. And we know that we're not in that list. So I have to assume that some of the large deployments like CERN and some of the other hosting companies out there that are running OpenStack might be reflected in that number. So in summary, not many OpenStack clouds are using cells v2 to its maximum benefit. And truth be told, not many deployments probably would be good candidates for it either.
On this slide, we talk about how we actually accomplish deploying cells v2 using OpenStack Ansible or OSA. So we're back at Rackspace. We've decided cells v2 is the way forward for this customer. Rackspace uses OSA to deploy its Rackspace private clouds almost exclusively, if we're talking Ubuntu. So then we had to say, okay, OSA does not have native support for cells v2. How do we make this work? So we talked to the customer, we gathered the requirements, we made our recommendation. They said, okay, let's go ahead with a POC. So we started a POC with a master control plane and then 1,000 computes behind 2 cells. The first iteration of this was simply us just hacking on OSA, running playbooks using command line overrides. So we had a whole bunch of -e's, changed the host group to reference this cell when deploying these services. It was completely error prone, and one human error or a fat finger on a command line could have negatively impacted the cloud. So we said, yes, it's possible to do, but this isn't really sustainable. So as we kept going, we started looking at modifying OSA around host containers and container groups. So like default host groups and container groups. One of the powerful things of using OpenStack Ansible or OSA is that you can regroup hosts or make a custom host group and then assign specific services to that. So during the POC, we didn't have any of this, right? So when I was deploying Nova to the cell controllers, it got all of Nova, like the placement, the schedulers, the APIs. And we were doing a lot of post-installation cleanup to disable those unneeded services at the cell level. As we kept adding cells, because right now we're up to 15 cells, James, I forgot to mention that on the slide. We just added one last week. That we are, every iteration of adding a cell, we have taken the opportunity to refine both our installation process, like our run book, as well as our OSA knowledge around custom host groups and container groups. And I'm proud to say, as it stands right now, I can run setup OpenStack, which is an OpenStack Ansible playbook that installs everything, right? Like it'll install all of the component services to where they belong against a new cell controller group, and I will only get the services installed that we need. That was this is probably a good year-long effort of us tweaking OSA, learning where we went wrong, correcting our mistakes, and moving forward.
Yeah, and I do want to point out that these weren't necessarily changes to the upstream OpenStack Ansible project, right? These are changes to the way in which it's deployed and the extensibility that it provides with the Ansible, container group files, host group files, and some of the other extensibilities like extending HA proxy to lay down new VIPs for the cell controllers versus the master control plane really kind of speaks to how the forethought of the developers of OpenStack Ansible, right, to make it as extendable as it is, but then also, highlights the sort of lack of maybe upstream documentation that would have helped us a little bit earlier in the process to lay this down sort of correctly the first time. And as an operator-driven offering of OpenStack, it's up to us as operators to continue to iterate and improve that product to make it easier for others in the community to consume and contribute to.
Yeah, with that in mind, James, now that we have a pretty solid working understanding and knowledge of how to deploy Cells v2 with OpenStack Ansible, James and I's next step is we need to write a white paper around this so we can get this information out there to the community, and perhaps there's better ways of doing it than what we decided, right? And we can learn from that as well. And just to further James's point too, is we actually had to make 0 OpenStack Ansible code changes to make Cells v2 a viable option just with using our default host groups and container groups.
Great. So with this slide, we just want to highlight some of the considerations for the actual deployment and architecture. And I'll let Chris go into that a little bit more here.
Yeah, so when we started with our POC, we had only started with the 3 controller plane nodes in the MCP, right? Plus the 2 HA proxy or load balancing nodes. That worked very well with the 2 cells, 1,000 computes. There wasn't any real load issues, sustainability issues, or any issues in general, really, beyond just how we deployed it. But as we started growing, we put in an artificial human gate, let's say, that every 1,000 computes we add or every 2 cells, we pause for a tuning and review cycle. That was kind of a Rackspace-ism where we take a look at all of the components and how they're interacting with each other and see if there's ways that we can make improvements to stabilize the environment, speed up the environment, because API response times were a concern for the customer, but they weren't a deal breaker. They don't want the host list to take 2 minutes to return. But right now, if you do like an OpenStack host list in their environment, you'll get all 3,600 nodes returned with sub 30 seconds. So that was like not a deal breaker for them, but they wanted us to be conscious of API response times as we scaled out the environment. So once we hit 2,000 computes, I started to see some high latency and connection related issues around Rabbit and Neutron and Galera cohabitating on the 3 control plane nodes. So a decision was made to split those services out into their own dedicated physical gear, which then completely stabilized the environment, returned the API response times back to an acceptable level, and we continued on. One of the other things we noticed too was the number of connections to Rabbit at the MCP level exponentially grows with the number of computes you have, which is expected, right? Because at the cell level, the computes talk both to the cell controllers and the MCP controllers. And we needed that communication at the MCP level because we are utilizing designate in this environment as well. So we needed to know when instances were properly built. There needed to be a notification set to the MCP message bus that designate would pick up and do work off of. So right now, with 3,600 computes behind 15 cells, we have an average sustained connections of 35,000 to the Rabbit MQ layer or the message bus across all 3 nodes. Of course, that took a little bit of tuning. We had to adjust some U limits, and by putting Rabbit on its own dedicated gear, we can up the high watermark VM limit considerably. I think by default it's set to 30%. We up that to 70%. So we want the Rabbit process and the Erlang process to take all of the available RAM, on the physical node and run all of its queues out of memory for a speed issue, right, and a stability issue. We also saw that Neutron at 36,000 or 3,600 computes is busy, right? There is a lot of calls and a lot of check-ins that the services do to ensure that all of them are up and they're functioning properly. With the Galera side of the house, we really only see maybe 3,500 active sustained connections. And at the HA proxy or the load balancing layer, there's roughly 11,000 sustained connections at any given time.
Great. So it is important to note too, in this Cells v2 design, all user interactions for the cloud occur through the MCP. So that's going to be the area that you're likely going to need to scale out, sort of like we originally did in the reference architecture, where you can continue to break out the services into their own hosts as users and the cloud grow. If we cap the cells off at say 500 nodes a piece, we can sort of stamp those out and say, we know a 3-node control plane is going to work for 500 nodes, and we move on. But as Chris noted, as we continue to add capacity here, we're hitting scaling numbers that are introducing new problems to us that need to be solved. And we may very well find that there is a limit that has not yet been reached, but it might be right over the horizon, right? No pun intended there.
Yeah, we've anticipated 5,000 computes as being the maximum we can currently do. Before we would have to go back and do another almost like stability performance review, kind of like a pause. Let us take a look at all the things and see if there's any other way we can squeak more performance out of that MCP layer. But you're right, James. We planned for 5,000, but who knows? Maybe we could take this up to 10,000 with some proper scaling and tunings.
Perhaps. An important design consideration here for this particular cloud is the use of routed provider networks. So we didn't show a rack diagram, but all of these hosts live in the same data center, essentially, in a leaf-spine design where the layer 3 boundaries sort of exist at the rack and TOR level. So routed provider networks allows the cloud operator to segment out a network into multiple segments that are that exist at that rack boundary, where that layer 3 gateway is going to be different between every rack. We wanted users to be able to create their instances and specify a single network name or ID, and no matter where placement placed them in which cell they landed in, that cell was going to provide the proper connectivity to that network. So what I've reflected here in the table is that we have a network called public net, and every cell has a unique segment ID and subnet. So when a VM lands in cell 1, it would get an IP address from segment 1001, and a VM that lands in cell 3 will get one from 1003. There needs to be a common routing device to be able for those instances to communicate with one another. But from a user standpoint, it's all the same network. Security groups that are applied to instances, that occurs at the MCP, and all the same security groups can be applied all over the cloud. If you reference a security group, the proper IP address is applied to the security group rule on the compute node itself. So far this hasn't been an issue at all.
Yeah, and one of the main benefits of this too is we limited the broadcast domain. So by segmenting these networks, these large networks per cell, a broadcast storm from cell 1 won't negatively affect cell 3.
Okay, good point. Good point. A lot of the documentation you might find out on the internet regarding Neutron and specifically routed provider networks may be stale. So I do suggest checking out the upstream OpenStack documentation to verify caveats and supportability. As of Wallaby, ML2 OVN supports routed provider networks, ML2 OVS, and ML2 SRIOV, and Linux Bridge may also support it as well. This particular environment doesn't leverage Neutron routers, but instead VMs are placed directly on these VLAN provider networks, which we find the most performant configuration. So I look forward to somebody testing it with something like DVR or L3HA to kind of let us know how that works for them. So I am happy to say that, since this environment was first implemented, we consider the deployment of Cells v2 a success, right, in all regards. The cloud now sits at over 3,600 nodes, over 15 cells, and Chris and team have even managed to upgrade the cloud during that time with relatively minimal fuss.
Yeah, we currently have 221,000 cores running in this environment with across 11,000 VMs. But speaking specifically to the upgrade, that was a bit of a learning process as well. So when you have this distributed computational levels within your environment, which one do you upgrade first? That's something that we were talking about and chewing over quite a bit. And we settled on upgrading the MCP first, like we upgrade that MCP layer. We do a quick sanity check to make sure everything's working, and then we can roll through each individual cell one at a time. That was the plan. That is actually the current plan. The plan we did when we did the upgrade is let's just upgrade it all at once, but still stick with upgrading by groups. So in one weekend, we upgraded the MCP, and then we upgraded all 3,600 computes, and it took us roughly 48 hours to do it all. That really wasn't the best way to do it, though, because once that was done, we didn't necessarily have, since we were under such a time constraint, we didn't necessarily have the time we needed to validate each one of those distinct components post-upgrade. So yes, we blew through the MCP upgrade. That was pretty simple. Then we started on the OpenStack upgrade against all of the computes. That's a pretty long running process. I'm sure everyone knows. But problems started to pop up. So we were going from Stein to Train, and that was the upgrade where Neutron started using host aggregates within its networking scheme. Well, something happened during that upgrade where the aggregates weren't created correctly. So we started having some, I would say, Neutron server issues during this upgrade that we didn't notice right away. So in the future, like as a lesson learned from this, new upgrades start with the MCP, we pause a week, we do a full QC review of everything that's going on at the MCP level, and then we start upgrading the cell controllers. And there's no issues running the multiple versions of OpenStack at those different layers, as long as it's not forever.
Okay. So some of the issues, as Chris mentioned, we did have some Neutron-specific issues that we think relate to more of the Cells v2 architecture. And one thing we wanted to highlight here was a possible bug between Neutron DHCP agent and network segments. So what we found was that in the process of Neutron reserving ports for Neutron DHCP agents, it can sometimes result in an issue if a port is reserved for a particular network and segment, and it gets bound to another DHCP servicing the same network, but a different segment. So it may have the wrong IP address and can't respond properly to DHCP requests from clients. Replicating this has been a little bit difficult because we have not seen it as we deployed new cells. And once an agent sort of exists and isn't disabled, you won't have the need to pull a reserved DHCP port. But it is on our list to properly document and report upstream if we can replicate it in a more recent release of OpenStack.
Yeah, what are the
yeah.
I was just going to piggyback off that real quick, James. Yeah, so the issue happens. So say if a DHCP agent doesn't check in enough time, there is a setting in the Neutron server to consider that dead, or if it was removed from a network segment, the Neutron server will try and recreate a new one. Right, it ensures that we always have 3 of these running because that's the config. That's how we have configured Neutron server to run. So if it ever loses connectivity to one of these agents, it'll try and spin up a new one and reserve a new port. And that's where we were seeing this, James, is we would get out of whack, right? So it would try, when the code to bind the reserved port to the DHCP agent is run, it is not segment aware. It just picks the first one that sees as reserved _ something or another. I can't remember the exact name. And that may not necessarily belong to the segment in the cell that it's running in. So it seems like that's the bug that James was talking about, right? We just need a quick patch to say when it's looking for reserved IPs, please pick the one that's in the segment that you're running in.
Yeah, exactly. And additionally, we also found that the DHCP agent leases files contain all leases for all segments related to that network, whether or not that particular agent can handle those leases. So again, it seems to be another case of where the agent isn't completely segment aware because it's pulling all ports for a network and not really filtering out only the segment that it will service. So this ends up resulting in unnecessary memory usage for DNS mask and additional latency when the agent has to read in or update that leases file, because in our case, a DHCP agent will only service one segment, but we may have 15 segments because we have 15 cells. So, 90% of that configuration file is irrelevant to that agent.
And there is time when an agent restarts where it has to rebuild those host files. So, it's not as performant as it could be.
Right. So some things we wanted to reiterate here was in this Sales v2 design, if you lose access to the master control plane, you're going to lose API ingress and control plane visibility. Your data planes should continue to work in all cases. If you lose a cell, the rest of the cloud will continue to work, but you'll have limited visibility into that cell from the master control plane.
Yeah, and
additional.
Yeah, I would consider that the single point of failure with the Sales v2 design, James, is the MCP, the API ingress.
Yep, I'd agree with that. Some alternatives to a Sales v2 deployment might be leveraging a cloud management platform that can act as a high-level abstraction layer to multiple independent clouds beneath it, right? So imagine the standard reference architecture where you drop, a standard region with a 3-node control plane, everything's self-contained, and you drop 4 or 5 or 10 of those independent clouds, and then you have a CMP level that will orchestrate against those. That will certainly allow you to, in the case of the CMP failure, interact with the individual clouds individually. But the problem is keeping the consistency of things like networks and images and users consistent across all of those clouds would be a much more difficult task. You could, deploy multiple regions with each keystone updated with endpoints that specify all regions. So you could load balance the keystones and at least be able to reach most of them at all times. But again, keeping images synced across clouds, users, networks, et cetera, would be a real difficult task.
Yeah, one of the benefits of the Cell 2 design is we do have 3,600 computes behind a single API endpoint. And that that API endpoint is LDAP based, right? So it ties directly into the customer's auth mechanism. So there is a huge benefit in having just a single endpoint, but there is a huge benefit to what James is also talking about is by limiting your failure domains with multiple smaller clouds behind a CMP.
All right. Well, that's the end of our presentation. Thank you so much for inviting us, and we hope you learned something today. Thank you.
Okay, thank you, Chris and James. It was a great presentation. Thank you for joining us. Your efforts are very valuable to us. Bir alkış alabilir miyiz arkadaşlar? Teşekkür ederim. Thank you very much.
Thank you, guys.
Thank you. See you. Bye.
Evet, konuşmacılarım.
Yes, we would like to thank our speakers, and without giving a break, let us continue.